All right, so a few years ago when I was teaching econometrics, we lost a whole lecture from a once a week class because of a polar vortex day when the temperature was so cold they had to close campus. Anyway, I made this file to kind of walk people through some basic econometrics topics in place of that class. And I just came across it and realized there's a lot of things that my students in the upcoming term might want to see, kind of explaining some of these concepts. So um, some of these some of these tabs are things that I use in every class and I've shown elsewhere. For example, I've got exponents and logs. I take a variable and make it the exponent of x. You can see exponential growth. And then if you take the opposite, you take logs. Logs are flatter than exponents. I show some basic Excel formulas, things like multiplication and addition in Excel, and I show that elsewhere as well. And then I also show how log changes and percentage changes are pretty much equivalent, which is good for things like financial returns. So here I'm just going to basically show the regression tabs. Basically, I generated 21 random observations based on a formula that I calculated. And if you make a scatter plot of x and y, you'll see that y and x are positively related. The point of regression analysis is to find the relationship as a specific line through the points. And that's going to have a slope and an intercept, which is mathematically calculated. And that usually ordinary least squares is the first method to do that. You're basically taking the minimum square of the distance between each dot and the line. So we're going to find the best fit line through these points. So you can run a regression in Excel. I usually don't. But big things you see is where r squared comes from, and most importantly, the slope and the intercept of the line. And the other thing I point out is the significance. Remember, if the data are fuzzy, if there's a lot of error, you cannot tell with certitude that this is not zero because there's so much error in the line. And so basically, the error is almost as big as the coefficient, meaning that it's pretty likely that this crosses zero. You cannot say it's not zero. The intercept is significantly different from zero. You can see that it's got a very large t-value. But this is the slope, negative 679, and the intercept is positive 9.33. And if you take this line through, you will see that you have this slope and intercept form. This line passes through the points better than any other possible line you could put through those points. And right here is the negative, right? It's below zero, and then it's got the positive slope of 9. All right, so these red dots are actually the predicted values. For any value of x, you put it into the equation. You simply put x in here and you'll find a point on the line that is a predicted value. But it's not perfect. It's going to have error, sometimes known as a residual, where it is different from the actual value is different from the predicted value. And because every dot has that, you're going to get here 21 different errors or residuals. If you square them and sum them, you'll see that that's the value that's minimized. So this is what it looks like in practice. You have x and y. Predicted is simply plugging in that equation, right here, putting x in. And then the actual value, which was given, does not line up, and you're going to actually get the error term. Okay, so this is the residual, actual minus predicted here. So column AE is predicted, column AF is actual minus predicted, but also cell N22 gives you those numbers as well. Right. Now, I put this in when I had class. It's called an Easter egg, basically, to make sure students click through the whole thing. You always hide a question in there somewhere. And I said, plug in a number and come to class with it. A lot of times students don't read it and don't come to class with the answer. So here is the number is 900.5. And then you can see that if you put the formula in, and the formula actually comes from the regression output in O. Right over here, you can use the intercept and slope. You will You will see that the predicted number is 7,772. Now, if you were to look at the actual given numbers, 900.5 is not one of them, but 913 is. All right, and y is a little bit closer than that. All right, so let's look at that. All right, so if you put in the numbers, you'll see that you could actually look at where it falls on here. Excuse me. The number that you would get with that is predicted to be 7,722, and the number that's actually given is 7,839. All right, so again, that's, even though this exact number is not given, one is close, and the solution is close to the solution. So you can always tell you're on the right track if your numbers look plausible. Right? So that's kind of the point of this tab, is we made 21 random observations, found the line through it, plotted the line as well as predicted values, and then we can actually look at these residual or error terms. Now, in this tab, I take the same equation and I generate different types of data. I do this elsewhere too, so I won't spend too much time on it. But here is the equation 400 plus 9x. And you can see that the line's going to run through here somewhere with an intercept of 400 and a slope of 9. This is a little bit fuzzier. You can see there's more error. And here's extremely fuzzy and there's more error. Now, you can get that OLS slope and intercept here. And one thing we're going to see is that the intercept is close to 400 and the slope is close to 9. T statistic, which if you will learn in the class if you haven't seen it yet, is above 2 for both, so they're both significant. And R squared is extremely high. In other words, I made the data to be a pretty close to perfect relationship, and that's what those numbers show. But when I add error, I'm making that relationship less perfect. And now you can see that the intercept is actually not even close to 400, but it's pretty much could be 0. X is close to 9, and it is still significant, right? It's above 2. But R squared is a little bit lower, right? 0.8. And then the really fuzzy data, you can see R squared is extremely low, right? Or much lower relatively at least. Intercept is higher, but it is, again, there's so much error that you cannot say it's not 0. And the intercept is still positive, but it's further from 9. So the OLS line gets worse the more error there is. All right, so the last thing I want to show in detail is this. You're going to learn about where R squared comes from. Now, remember, textbooks sometimes will flip, and they'll have different terms for ESS and RSS. ESS could either be explained or error, and residual could be either regression or residual. In other words, they could be the exact opposite meaning. TSS is always total sum of squares, okay? And R squared is the formula of, depending on how you look at it, the way I have it here, is explained over total. And even I use different notation in different places. But I've got my X and my Y, right? And this is my predicted value using the formula. And here is something, you'll see it plotted here. Basically, this is what's called Y bar. This is the intercept plus, instead of having every X and having it change with X, you just put in one X. This is the average X across, okay? Now, so that gives you the value of 4,397. Sometimes you'll see this plotted in textbooks with different ranges. This is literally using the Excel data that I made, right? Now, ESS here is N minus O, is basically predicted, the gap between the red and the green, predicted minus this flat line here. And I believe it's, yes, squared, all right? And that is what could be called the explained sum of squares. Total sum of squares is M minus O. And this is Y, the actual minus the flat line, right? Minus the Y bar, right? And then RSS is Y minus predicted. It's between the dots and the red line, right? So that is what could be called the residual sum of squares. And remember, all of these are squared. All right, so there's two different gaps. So just to repeat, N minus O here is predicted red minus green. Total sum of squared is Y, the dot minus the total, or excuse me, dot minus green. And then you are looking at the RSS, which is, get it here in the formula M minus N, which is dot minus red. So essentially you're taking the big distance from the blue to the green, from the dot to the green, and you're splitting it up into two parts between blue to the red and red to the green and seeing what proportion that is. Now, if they were all on one same line, there would be no gap, right? That there would be no gap here if they were perfect. Kind of like over here. This is like a perfect relationship. There's no difference between the actual value and the predicted value, right? The bigger the gaps are here, the lower R squared is going to be. The smaller the gap, if you move this blue dot down to the red line, there's no error anymore. That would be perfect prediction and an R squared closer to 1. Right? So where does R squared come from? Well, it's right here. You take the sums, ESS, right, explained sum of squares, divided by total sum of squares, right? So, and then you divide, and remember, if these are equal, this is going to be 1. In other words, your regression is explaining all of the variance. The lower this sum gets, the lower your R squared. Your regression is explaining less. All right, so R squared is the proportion of explained over total. And if you do that with these numbers, you get 0.85. This regression explains 0.85 or 85% of the variance. And that's exactly what we saw in the regression before. So that was in the regression output. Okay, so this kind of explains where R squared comes from and explains the explanatory power of the regression. Now, I do have this tab. I take, this is the Keynesian equation. This is consumption related to output. These are time series data, and actually these would be non-stationary. I wouldn't really do this regression, but if you look, consumption and output have a linear relationship, and if you looked at that, the slope would be marginal propensity to consume. So what I have here is do a regression of consumption, real consumption on real output. Now the C here stands for constant. This is not consumption, but the Y variable is consumption. So the slope is 0.64, and that estimate would be your marginal propensity to consume. And you can look at it here. R squared is super high. Coefficients are super significant. That is because this is it's non-stationary. There's some sort of spurious regression. If you take time series analysis, you would learn to do a different modeling approach. But here you can look at it, you can see that you could estimate that Keynesian line. Now, so to recap, right, I'm pretty much laying out where the OLS line comes from and tying it in from starting with real data, going through regression output, and then showing how the data line up with those points. And then secondly, I show where R squared comes from, with the explained sum of squares, total sum of squares, residual sum of squares, and this proportion gives you how much of the relationship is explained by your regression.